Assalamualaikum warahmatullahi wabarakatuh and good day. So in this video, we continue with consistency with theorem 9.2. So suppose that we have theta head n converge in probability to theta. Okay, this one. And that theta head prime n converge in probability to theta prime. Okay, so you can see we have theta head n converge to theta. And then we have theta head prime n converge to theta prime. So A, if we have theta head n plus theta head prime n, it will be converge in theta plus theta prime. Okay. And then if we have theta head n times theta head prime n, so this one will converge to theta times theta prime. So if theta prime not equal with 0, so if theta prime not equal with 0, theta head n over theta head prime n is will converge to theta over theta prime. Okay, so in this case, the denominator is not equal with 0. Okay, if g function, okay, is a real value function that is continuous at theta, then g theta head n will converge to g theta. Okay, so that's the theorem 9.2 actually to make your life is simple and easier. That's mean if you have summation of two theta head n and theta head prime n, so it will be converged to the same thing, theta and theta plus theta prime. Okay, so notes here, we can prove, okay, theorem 9.2 closely. It resembles the corresponding proof in the case where we have an and bn a sequence of real number converge to real limits a and b. Alright, so for example, if an goes to a and bn goes to b, then an plus bn will goes to a plus b. Okay, this is how you prove for a, b, c, and d. Okay, by this concept. Alright, so now look example 9.3, page 452. Suppose that y1, y2, yn represent a random sample, so such that you have expected yi equal to mu and then expected yi square equal to mu prime square. Okay, if you remember this one, you've done this, okay, in method of moment. And then if you have expected y power 4i, that's mean you equal with mu prime 4 are all finite. Okay, show that the sample's variance, which is s square n, equal with 1 over n minus 2 summation times with summation of yi minus y bar n square. Okay, so this one given, okay, you have y1, y2 until yn, and then expected yi, this one, expected y square I is this one, and expected y 4i is this one. Okay, so show that sample variance is a consistent estimator of sigma square equal with variance, expected variance yi. Okay, so note here, they use subscript n on both s square and y bar n, okay, to explicitly convey their dependence on the value of sample size n. That means we use n here and n here because we consider we take it from the sample size. Okay, so how is it to solve this one? So this is the solution. So basically from earlier chapters, okay, in earlier video, we have seen that s square, okay, which is now written as square n here, is equal with this one. Okay, we have this one, then we can simplify or we can do like this. We can rewrite back like this, which is n over n minus 1 times with 1 over n yi square summation minus y bar square n. Alright, so the statistic 1 over n times summation yi square, okay, I from 1 until n, is the average of n independent identically distributed random variable. Okay, this one knowledge that you have before. Okay, you have learned this one before. And then you have expected y I square equal to mu prime square mu prime 2, and then the variance y square I will have mu prime 4 minus mu prime 2 power 2. Okay, so this is actually you get all that you learned from previous video or previous chapter. Okay, so by the law of large number, which is shows in example 9.2, Okay, we know that this one, okay, will converge in probability to mu prime 2. Okay, so basically here you can see that when you solve the question or this example, you use a previous knowledge, previous theorem. Okay, so sometimes you need to remember. Okay, so example 9.2 also implies that yn converge in probability to mu. Okay, because the function gx is equal with x square is a continuous for all finite value of x. Therefore, theorem 9.2d implies that y bar square converge in the probability to mu square. Okay, then it's follow from theorem 9.2a that 1 over n summation y square I ni minus y bar square n will converge to mu prime square, mu prime 2 minus mu power 2 equal with sigma square. Okay, maybe it's quite too fast, but you can see that here, okay, from here we have this one, okay, and you can see that from here we have this, okay, this one summation y bar. So this one you can see this is gx, which is x square. Okay, so this one is a average of n independent identically distributed variable. Okay, and then you can see here y square I is mu prime 2, so that's why we have here, okay, this one, you will have this one. Then when we have function, okay, and then gx actually y bar square, so this one will converge to mu square, mu square. All right, and then 9.28 is a summation. Okay, you can see here summation. When we have summation, which is here, you have, okay, so here what is it? This is mu prime 2 minus mu 2. Okay, this one. All right, then this one will give you sigma square, which is this one actually s square n, isn't it? Okay, so because, and then this one we cater about this part. Okay, this part. Now then another part, because n over n minus 1 is a sequence of a constant converge to 1 as n goes to infinity, we can conclude that the sample variance converge in probability to sigma square. So equivalent sigma square, s square, okay, the sample variance is consistent estimator for sigma square, which is the population variance. So you can see that we don't have any calculation here, but there's more to understanding, how you understand the theorem, how you understand the flow of the subject name. All right, in order for you to check, okay, to show that this sample variance is converged to sigma square and is consistent estimator, you use many things that you have done or you have learned in previous chapter, in previous video, in previous subtopic. And then with additional of the theorem 9.2 ni, you can solve the example using justification and assumption. All right. So now we move to theorem 9.3. So suppose that un has a distribution function that converges to a standard normal, okay, as n goes to infinity. If wn converge in probability to 1, then the distribution function of un over wn converge to a standard normal distribution function. So this one actually you done for in chapter 5 as well. Okay, in chapter 5 as well, but at the early chapters, early videos, you can see that when we have u follow standard normal and then w is converge in probability, then when we have the ratio of this function, we converge to a standard normal distribution. All right, so you can see from example 9.4 here, page 453. Okay, so suppose that you have y1, y2, yn is a random sample of n from distribution with expected yi mu and variance yi equal to sigma square. Define s square n as this one. Okay, that's been shown lah. So basically you can see that the distribution function, okay, you have this, and then show that the distribution function of this one converge to a standard normal distribution function. Okay, so you have this s square, which is we know that this is the sample variance. Okay, and then we have this one. We want to show this distribution converge to standard normal. All right. So how is it? If you look, or if you remember in example 9.3 previously, we show that this S square n converge in probability to sigma square. All right. And then notice that you have function x equal with plus minus square root x over c. Okay, it's a continuous function of x if both x and c are positive. Hence, it follows theorem 9.2d that this one will give you s over sigma equal with plus minus square root s square over sigma square. Alright, so you can see that we implies this one into our situation. So this one will converge in probability to 1. So we also know that from central limit theorem that you've learned in this chapter, previous video, that the distribution function of un, which is this one, okay, will converge to a standard normal distribution function. Okay, therefore, theorem 9.3 implies that the distribution function of, okay, you have un over wn will give you this one. So this is what? This is a standard normal distribution function. Okay, so that show you how is it. Alright, so again, I want you to go through again all the example and then look, do you understand or not? How is it? Okay, but you must clear that in order to solve the example 9.4, 9.3, you should remember or you should understand the previous knowledge. Okay, so for example here you can see like central limit theorem, and then we have this this function. Alright, so try do again all the example, okay, and then do more exercise, okay, page 454, and then if you have any question you could ask me. Thank you, class.